Okay, so let's take a look at how we insert a node into a binary search tree. Inserting a node is actually a lot like searching for a node. So what we know is that when we insert a node, it has to obey the binary search tree ordering rules. So what was that? A parent has to be greater than or equal to its left subtree and less than or equal to the nodes in its right subtree. So we have to obey that ordering when we find a place to insert. What happens? Well, if there are a few cases we need to think about. What if there's nothing in our binary tree yet? Kind of like if we have an empty linked list. Well, if we have an empty tree, then the first node we insert will become the root of the tree. So that's an easy case. We don't even have to do any work. We just know the tree is empty, root is equal to null. We just stick that new node right there at the root. Okay, otherwise, we have to decide where the new value falls ordering wise with respect to the nodes that are already present. And so we're going to insert lesser values to the left subtree or greater than or equal values to the right subtree. And so a convenient way we can do this is that we basically use the same logic as a search to look to see where should the node be in the tree. And then we just insert it there. Once we get all the way down to the leaf of a tree where we would expect the node to be, then we just do the insertion at that point. So here's an example. We're going to kind of first figure out where would 8 be. So we compare 8 to 9, and that means we have to go to the left because it's smaller, but 8 is bigger than 5, so we go to the right. And then we know that 8 is bigger than 7, so we need to go to the right again. And so, but there's nothing down here beneath 7. So what we need to do is insert the new node here to the right of 7, right? So the search would have sent us down this path, and then we capitalize on that, and we just add 8 to be the right child of 7. And this, what I've written over here just summarizes this process. Since there's no right child on 7, we can just insert 8 at that location. Here's another example, 22. We already did this once before. So just like with searching, I'm going to look to see where would 22 belong in this tree. And so it's going to send me down the right side of this tree. But then when I get to 16, I realize 16 has no right child. And that means I can make 22 the right child of 16. Okay, so here's what our pseudocode looks like for inserting into the binary search tree. If my root is null, then I can just insert here at the beginning. And so I'm assuming I've already made the node, allocated the node. And so I'm just going to set root equal to my new node and then set left and right equal to null. And this is my base case. And if this is my first node, there's nothing else to do. I just stop. Okay, but if I insert node and there is something in my tree already, and then what I'm going to do is something that looks a lot like a search. So I'm going to get a temporary and point it at the root of my tree. And then I'm going to have this while loop that loops down over the nodes of the tree looking for where my new node could belong. And I'm going to say, well, is the data in my new node less than the data at this point in the tree? And if it's less, that means I need to go, to the left side. So if node left is null, then that means I can just insert the node right at that place and stop. But if it's not null, then I need to advance my pointer to the left node and then do this process again. Okay, else, if the data is greater than or equal to temp data, right, the node I already have in the tree, then I need to put it on the right. And so if the right side pointer is already null, I can just insert the node right there because I know it goes to the right and I don't need to do any more work. But if that right side pointer isn't null, then that means there's a node there and I need to go to that node and do this whole process over again and decide, well, which side of this next node should my new node belong on, right? And so this while loop will run until I find a node that doesn't have a child on the side that I would want to insert this. And eventually I have to find it because eventually I'll get to a leaf node if nothing else. And then I'll insert my new node either on the left or the right side of it, depending on its value. Okay, had some notes here, but I forgot about them. Right, so when we find a null child, which we're bound to do eventually, then we're just going to insert our new node here. And we're either going to insert it on the left side or the right side based on the relationships of the data. These two lines of code basically mirror each other and are almost exactly the same, except that one is inserting on the left and one is inserting on the right. Okay, now if we look at the time complexity of these binary search tree operations, we already talked about search having big O of H. Well, now that we've looked at how insertion works, we know that insertion is basically just a search where you then add a node on to the very bottom of the tree. And so that means it's order H plus a few extra operations to add on a node. And those extra operations are basically O1 because it's just allocating a new node and then setting the pointers properly. And so that's O1. That extra cost to allocate and set the pointers properly is an O1 cost. And so that means it's, order H plus order 1, which is just order H. So inserting a node is the same cost as searching. And again, if our tree is completely full, and that means that order H is approximately log n, where n is the number of things in the tree. So inserting a node is efficient. If we wanted to insert n nodes in the tree, then the cost is something like n times h, where for every node we're inserting, we have to pay at the worst a cost proportional to the height of the tree. And if h is really log n, then this total cost becomes something like big O of n log n. Okay, so in summary, new nodes must obey the binary search tree ordering rules. If it's the first node we insert, it becomes the root. Otherwise, we insert the lesser values to the left or the greater than or equal values to the right. And we insert at the first node we reach that has a missing child and that satisfies all of our ordering rules. Insertion achieves the same big O of H efficiency as search does.